Yeah, it's it's fine.
Yeah. All right, let's begin. Any question before we start? X and Y. X is for stochastic. Smaller or X. Last time a mistake, I put a less than equal to sign. So this is the probability of being less. So X is actually smaller. Equivalent, you can think of P of X greater than X. P of X. This is much easier to think about. Which one should be larger? We'll simply going to denote this by X. So now the first thing we'll do is to somehow couple coupling with stochastic. This is clear. The definition is clear. Can you give an example where X is dominated by Y? That would be able to clear up things. Give me from 0, 1 and from 1 to. For example, X is uniform between 0 and 1. Y is uniform between 0 and that's what I'm saying. So, what is the probability of X being less than little x? Little x. Same is true for y being less than x. Try to do it. If x is between 0 and that's positive. So this is true for x between. This is true for. No, it's right to. Probability x is less than 1 is half. Okay. So now this is larger than this. Y dominated. No, so x is dominated by y. See, I told you to look at which direction. See, x is smaller, larger than x by 2. Yes. So since I want to be larger than. Okay. So remember, this is a weird sign. What are we trying to control? what is the probability that x is smaller than the value given x? So this is larger in some sense. That the likelihood that x gets smaller value than y is larger. Okay, that's it. But if you want, you can think of it. What is the probability of x taking larger than value given x? Any other example?
Yeah, binomial.
What is coin toss?
And
Think of a coin toss. Will you come with an example of x and y, such that x is dominated by y? Or an indicator random variable. Okay, put two indicator random variables. I1 and I2. You only take values 1 and 0. So put some probability for this and put some probability of this. What about the output? Let's say this is the probability of B and this is the probability K. Now, let's say P is smaller than K. Does I2 get dominated by I1 or is I1 dominating I2? What is the probability of I1 equal to 1? It's a discrete random variable, so that you can equivalently look at probability of capital X equal to little x. Is there something you're not clear? Tell me what it is.
That indicator one, its value is one when with probability P or when
With probability B.
okay.
There is no other way of defining it. Is there any other way of defining it?
Like if X belongs to some set.
Don't care. That's more complicated way of describing it.
Okay.
It takes value 1 with probability P, it takes value 0 with probability 1 minus. As simple as that. Two coins is equal. X and tails. X is 1, tails is 0. Now does I1 dominate I2 or I2 dominate I1? That's all you have to understand. Tell me which one is the right direction. What does the intuition suggest? Which coin would you pick if you would like to, let's say, you're going to win with the heads and heads is 1. Which coin would you pick?
I2.
Okay. Why? What is it in terms of?
It has higher probability of getting
Of winning, right?
win.
So it's just complement the set. What is the probability that I1 equal to 1? It's P. What is the probability that I2 is equal to 1?
Q.
Which one is larger?
Q is
Okay, so
I2 equals to.
so which random variable dominates the other random variable?
I1
I1
dominates I2 means as per the definition.
It's opposite, right? I1 is getting dominated by I2.
But can you go to the previous?
Who is more likely to produce smaller values? Think of it that way. X is called stochastically smaller or dominated by Y. So which one is I1 is getting dominated by I2 or I2 is getting dominated?
I1 was dominated by I2.
Now is it clear? If there is any hesitation, I would like you to say it rather than holding it. Okay, now let's try to do the following now. So if X is stochastically dominated by Y, then dependently there exists a link X hat comma Y. Pretty that x hat is less than equal to y. So the particle. Okay. So you see, if and only if statement. That if x is going to get stochastic, if x is stochastically dominated by y, then there exists a coupling x hat y hat such that the probability that x hat is less than equal to y hat equal to. It's only there exists, not for all couplings. Very important. Because for x and y itself, see, x y itself is a coupling of x y. It's a trivial coupling, but that need not satisfy this condition. I'm just saying there exists one, so we produce one. Okay, so which direction is easy? One direction I claim is easy. So suppose you're given which one is easy? Think about it, which one is easy? So suppose there exists an x hat and y hat such that probability of x hat less than y hat is 1. Can you show that x is stochastically dominated by y? So starting point is that. And remember a definition of coupling. What does the coupling mean?
They will be having same tissue.
Marginal distribution. That's all. There's nothing more to exploit. We are given this condition and the fact that x hat y hat is a coupling. Is there a recipe to do this? So we fix some small x. Okay. So you don't need any sum generally. We just begin with this. You know this. True. Yeah. This is given to you. And the fact that x hat and y hat is a coupling. All you have to produce is somehow show that this is true. So let's start with one of the sides. So what is P of y given as? This is the clear cut clue on how to proceed. Let's begin with this side. I want to show that this is less than equal to. This is equal to what in terms of coupling?
Probability of y hat is less than equal.
It's just because the fact that y hat is state distribution. So P of y hat less than equal. Now I somehow want to use this. How do I introduce something like this inside this? So using that fact, what more can you write this probability? You know that probability of x hat being less than equal to y hat is 1. Using that fact, what can you write? P of y hat less than equal to x as a function of both x hat and y hat.
This will be greater than equals to probability x hat less than equals to x.
Both directly is not here. True. Then what do you want to do?
Greater than equals to.
Okay, that much I can. How do you suddenly jump from this to that? All you're given probability of x hat less than equal to y hat is 1. Why does this imply this?
X hat is smaller than y hat, that thing we know. And y hat means that probability is implying that what's the probability of y hat being less than x? So that thing can be. Wait.
Is it going the right direction? So this is a question mark here. Let's proceed. If I write this, is this okay? given the fact. Okay, it is the same event type. Now what does this mean? This is at least at most exact works. By definition. There's nothing more events happening on the left hand side. Okay. And what is this quantity?
X less than X.
By definition equal to
Why did that inequality came?
from here to here.
Okay, that can be written as sum of two different probabilities, and this is one.
What is this?
X hat is less than equals to y hat less than equals to.
So there are two events.
Hmm.
If I drop one, what happens?
Probability.
That's all. Okay. Reveal the equal.
Okay.
So I keep that question mark as it is. I don't think that is correct. The thing is going the wrong direction. So this forward direction, knowing that the probability of x hat is less than y hat is equal to 1, we have that is stochastically dominant. More interesting is what happens in the reverse. Answer question. Okay. This is slightly more important. For that, we need to follow. So suppose f is some distribution. Yeah. We'll define f inverse of u to be since to
When you using 0, 1 and
yeah, using zeros.
smallest.
Because that's where f is defined. Is the definition clear? So what is the f? F is a map from where to where? What does f take value?
R to
R to 0. Right. So you pick a u belonging here, and I want to go back. Okay. That's precisely. See, what was this was p of x less than equal to little x. That's what effects of x was. Yes. So all this mass was getting mapped into f. I'm just inverting it now. If it is needed. That's okay. Now think of u, capital U. U the uniform random variable. What do you think I'm playing at now? I want you to find out the capital U. The distribution of f inverse U. We use a random variable. F becomes nothing but a map. So this itself is a random variable. For the moment, we are not worried about measurability, but again, let's know that this itself is a random variable. What is the distribution function of f inverse U? It is simplest f. Whatever you think of. What would f inverse of u look like? It's difficult to visualize.
In terms of F, right, the answer will be.
Yeah, in terms of M, of course. That's the only thing remaining. Because U is a very nice random variable. It's a very standard result, but I'll still ask you to think about it. So take an example of F. Take the simplest example of F, and at least for that evaluate it. Go to simplest F.
X between 0 and
Why that complicated? What is the simplest F you can think of?
discrete.
It always takes value 1. A random variable, it always takes value 1. What is F for that? 0 everywhere except for that 1 and those 2. No, nothing of for that function. What is F inverse U going to look like? To take any point U, where does F inverse U get mapped?
It will be 0 for all.
Example F is 0 and suddenly this is value 1. Now what is the F inverse of U? Pick any U. Or I don't even call capital U, just little u. For any U, what is the input value for which F of x is greater than equal to U?
What? First, we U is equal to half one.
Let U equal to 0, simplest starting point. Why take any difficulties? Okay. So what is F inverse of 0?
Minus infinity.
Okay.
If U is positive, then it's good.
So do yeah, go on.
Yeah, sorry. That is F inverse. Minus U here.
Okay, let's try to prove what happens and then we'll come back to it. It has the same distribution as that. So what do we know? Want to control probability of F inverse U. What is this equal to? So what will these two are equivalent. No, tell me. Something is not clear, don't stare at the board, tell me.
Are we writing this after assuming that F inverse of U has any distribution that?
No, we're trying to prove that. Okay. This is the distribution of F inverse U, that much is clear. This is equal to this. Forget the rest of the board, let's look at this equation. This is equal to this. Whatever done, just move the F around.
Okay. Yes, yes.
Some care is needed, but let's suppose that this is true. Okay. Oh, now what am I? U is a uniform random variable. So what is this value? What is the CDF of uniform distribution? X itself. So Move these 2 lines. We think it correctly. From here to here, if you think it's a jump, that means yourself consider. By the definition of what I meant, it's perfectly fine. If everything was continuous, no problem anyway. It's just that I possibly have discontinuities. That is why you have to be careful. If there is no discontinuity, you should not have any problem. Just that because F could have discontinuity, one has to define all this. And make sure that it works. The proof is actually 2 times. I thought it was a standard that. And do you know that F inverse on its own has uniform distribution?
What is that?
So F inverse can be treated as a random variable. Try doing this. It's also between 0 and 1. It's a map from 0, 1 to 0, 1. That's the uniform. Okay. So we have this. Now what do I do? What do I need to show, remember, is that there exists a coupling such that probability of x hat less than or equal to y hat is 1. How do you do this? If I know this result. So you have now produced x hat and y hat. What are the candidate x hats and y hats? It's just obvious now. This is true for every distribution F. And remember, you are given x and y. So if you were to use fx inverse u and fy inverse u, they have the same distribution as x and y. So they are candidate couplings. Question is, what do I want? Do they satisfy that relationship?
So we have that X is dominated by Y. I want to show the existence of X hat Y hat. So if X inverse uniform is same as X.
Sorry, go on.
Fx.
So I can play this with fx and fy. So my candidate x hat and y hat are simply fx inverse of u and fy inverse of u. That one is clear. Right. Yes. These candidates are clear. So existence is somewhat. Now, what we've shown is that x hat is a coupling of x and y hat is a coupling. Same distribution as y. That much we know. Now all we have to establish is this is it. How do we show that? So x hat okay. So what is stochastic now? X and y are stochastically connected. So x is y. What does that imply? That f of x that's just by the definition. So what? So what about fx inverse u and fi inverse u? What relationship do they hold? The reverse relation. Right. Am I clear that I'm done? Give me the punchline.
These are the X hat Y hat.
Exactly. So for all u they are true. So with probability 1, it's true. So for this x hat and y hat, this implies that it's a nice coupling and stochastically dominated analytics. Because it's not so whatever we presume that this must be stochastically dominated by that, it's actually difficult to actually prove things like that. Last time we looked at one example. Bernoulli with n trials and Bernoulli with the same probability and 2 n trials. One would expect that a 2n guy always produces a result which is larger than the first one. But if you're tossing coins separately, it's very difficult to compare. But what you do, you take the same underlying random space and just take the first n by 2 into one of them, all of them into another of them, call them x hat and y hat. Now we know that this coupling definitely has probability of x hat less than or equal to y hat equal to 1. So it must be that the x is stochastically dominated by y. If you did not have this theorem, you would not be able to. Okay. Go over that quickly here. What was the example last time we saw? X is n of p. Welcome. You would like x to be dominated by y. If there is any justice in this world, you would like that too. So how do you actually show it? But if you do this experiment today, do the experiment tomorrow, you see different results which are incomparable things. Instead, you produce x hat and you produce y hat. What would be the right quantity? You can simply say, I'm going from 1 to 10. Say, where ij 1. So I can do this, and at the same time, I can do this. Now they have the same randomness sitting. I'm just tossing these coins. Whatever results I see, I count here. Whatever results I see, I count here. So it's necessary that probability of x hat being less than or equal to y hat is 1. Because whoever is here is also always here, and they're all non-negative. So definitely, probability of x hat is equal to y is 1. And we know that x hat has the same distribution as x. So this theorem empowers us to reach this out. Now what about Poisson? So take x to be Poisson lambda, y to be Poisson. Where lambda is equal to mu. What do you want to say? And how do you actually say it? Again, you would expect x to be, now it's opposite, x to be dominating y. Right? Lambda is greater than mu. So very likely you will see more numbers with x rather than y. How do you show it? What is the right coupling?
X you can write as sum of 2 Poisson.
Okay,
First with mean mu, second with lambda.
Let's say x1 plus x2. This guy is what?
Mean mu.
So Poisson will mean mu, and this is lambda minus mu. Yes. Okay. And IID, sorry, independent. X1 and x4 independent. So definitely x is a Poisson with red lambda. Okay, now what is y at?
X1.
Simply x1. Now, is the distribution same? Yes. X is the same distribution as x hat. Because if you take union of two independent Poisson, it gives rise to another Poisson with the sum of the reds.
So x hat has the same rate as x, and y hat definitely has the same rate as mu, which is again equal. So y hat, so x hat y hat is a eligible couple, satisfies the requirement. Now, what is the probability of x hat being less than or equal to y hat? Again, the same story. There is a common randomness. X2 is not negative. So whatever the value of x1 is, y hat is, sorry, whatever the value of x1 is, x hat is always greater than. So again, we can. So this is the very simple result, very powerful one to show dominance.
So this is some in between stuff which will keep appearing once you actually get to random numbers. As bias. Right. So let's say x is a random variable. Its size biased and counterpart. And keep using x star for that. How to define as star specific x as a expected value x indicator x. So this will come in essentially sampling. So when you're looking at a random graph, if I tell you something about a degree of one particular node, it biases the degree of that node itself. Essentially, some conditional distribution is what is going to be. But for the moment, it's just an abstract definition. You have a random variable x. You want to define its size by a distribution. Maybe there's this one. So, any comments about this? Can you compare x and x star anyway?
The numerator is probability x less than x, right? Probability x less than x. Yeah. So it takes value x only when x is smaller than little x. Otherwise, it's a. So if the expected value of x is 1, then they are equal. Yeah, that's not interesting. Compare x and x star somehow. And like if I give you two random variables, what is the first thing you always do? You don't go to stochastic order. What is the first thing one looks at? The expected value. So what do you think the expected value of x star is compared to expected value of x? Expected value looks like 1 of x star. Always. That would be very strict. I thought the denominator will normalize it. No, but that left hand side quantity is not the expected value. Oh, yeah. Expected value, if you want to look at CDM, is 1 minus the CDM. So expected value is summation of P of x star greater than or equal to x, summed over all x. So before that, maybe let me ask, if x is stochastically dominated by y, what do you think is going to happen to the two expectations? What is the expected value of x compared to expected value of y? Expected value of x is dominated by y.
expected value of x is less than.
How do you show that? You have the solid result now, the coupling result. You do not use that. What does coupling tell you? The probability of x hat less than or equal to y hat is 1. So what does it mean in terms of their means? At least for x hat and y hat, their expected values are in the right order. But x and x hat are the same distribution. So it must be that the expected value of x is less than or equal to expected value. Okay. So there are that theorem is very powerful in showing. Otherwise, you can just stare at it. Why should it be? All I'm saying is that CDFs are controlled. Why is the expectation also controlled? But given that the coupling result is there, so use that. So I have no idea about x star and x, any relation between x and x star. We're going to prove there. X is not just an expectation, much more strong. See, stochastic domination implies expectation. The expectation implies stochastic domination. So counter result. So X. It's X. Remember this stochastic domination definition requires for every little x that has to be. So any example for this?
Yeah, so the uniform 0, 1 and uniform half equal.
X is
X is the uniform. Split make it 0, 10. Y is uniform 5, 8. 5,
0, 5.
bit 5 and 8.
5 and 8. Then will work. Why should there be 8s? And put 8, but whatever you're trying to do should be.
Mean of Y is more than mean of X.
But even if I put 10 here, still going to be true. Okay, now why is it that X is not stochastically dominated by Y? It should not work. But is it clear what we're looking for? Either you prove the fact or disprove the fact. So if you can produce a single random variable where the expected values are going this way, while X is not stochastic. What should they think? Don't give me an example. Think about what has to happen. There at least there's one place the CDF has to have the reverse direction. So for that to happen, what kind of a random variable you have to look at?
We want this probability of
Yeah, y could for here, y could be uniform 2 5. Sorry. 0 5 make it 2 5.
okay.
Mean of x is small, but none of them dominates it. But x does not dominate it.
So select small x.
5.
Okay. So what is the p of x that is equal to 5? Just 5. So that's half. What is the probability of y less than 1? It is simply 1. But what do you want? You want this guy to be larger than this guy's mean is larger than y. But it makes it to be dominated. Sorry. X. But E of y is not greater, right? What is that? It's actually smaller. This is not a concept.
Where x equal small x equal to 2 words.
Small x equal to 2.
For y is 0. I mean, basically, let's intersect.
You have many ways to construct this one. Oh, now what is that? 1.
2 by 10.
What is x larger than 2? It is 2 by 10. 0. 0. Now what is whose mean is larger?
X.
Mean of x is larger. Always. Now the direction has moved. So there are many ways in which you can connect them. So expected values are very crude estimate of random variable. You can't say my average is larger, I have a better random variable. Essentially, you can also play around with zeros. You want discrete distribution. One of them takes 0 and put sufficient marks there. Because it will pull the expectation down. But then once there is sufficient probability, you can put it on the right. Okay, so now coming back to the side bias. So what do you want to show? X is weaker than X. For that, we will give the intermediate lemma. You might have seen this. So that F and G and G2. This lemma is useful for many other things we'll do like. Then expected value of FL. Yes. Probably right.
Cauchy Schwarz image.
Cauchy Schwarz will put square roots at that. Similar. Actually, Cauchy Schwarz both are less than equal. This is only for f and g. Essentially, think of increasing functions, not decreasing in this direction. So again, as always, I do this. Any example which comes to mind for this is true. Where f and g are identically 1. That is what is called f of x goes to x. We name such function. Identity. Suppose f and g are identity functions. Then clearly this is true. Expected x square is greater than or equal to expected x whole square. Now tell me something non trivial. But it's not an identity function.
or refute it if you think it's not true. Pick a random variable x, pick f and g such that this is not true. But make sure that f and g satisfy increasing criteria. If both functions are increasing. F of x equal to x, g also equal to x. So that anyway works. That's why I say identity.
Identity is constant. Okay, now
Identity means f of x goes to x. Any other function for which this is easy to see? You can't take x and 1 by x. That's not a because not decreasing is not by decreasing. So suppose I take f equal to g inverse. What happens to this inequality? Is this still true? For example, f is x and g of x is 1 by x. The left hand side is identically 1. What can you like? Can you make the right hand side more than 1?
are we talking about general functions or
So
basically?
just try to one fixed function which does not satisfy the property. They're not both non-decreasing. Is this inequality still true or not? So f of x is x and g of x is 1 by x. So left hand side is just simply 1. Now can you produce a random variable x for which the right hand side is more than 1? That's all you have to do. So zeros are out. It's like the random variable cannot take a value 0. But close to 0 is fine.
But 1 by x will be decreasing function.
I know. I'm not saying that I'm proving something. I'm just trying to see if this is true for a function of the type which does not satisfy this. So can you make the right hand side larger than 1? Where f is x and g is 1 by x. So all you have to do is to specify a particular random variable x. Give me a choice of random variable x. I already said something like if you allow x to take a value 0, what is g of 0 going to look like? Infinite. So even if you avoid the degeneracy, you take very small value close to 0. So the right hand side is arbitrarily large. So this better be not true. So it's needed. Unless I'm putting the part. If they are going in the reverse direction, something else might happen. There is actually inequalities of that type also. One is intrinsic, other is really what happens. Currently, both are incompatible. Okay. Moving not actually. Let's say x1 and x2 are distributed as x and independent. Same distribution. Then we have x value. And x1. Is this okay?
So what should I do now?
Okay.
I can use the independence property. X1 and X2. So let me write expected value. Of X. X1 and X2 are independent. So I can write this. This is also true the other direction. Now we're essentially good to go. So remember what we need to prove. We need to prove that this quantity is greater than this quantity. Give me the how we discuss on this. Add, subtract, write it the right form. So if you subtract this quantity from this quantity, I want to show you greater than equal to 3. So let's suppose I subtracting this minus this. Okay, so this is going to be this correct. Yeah, which is added. Okay, now what do we do? Yeah, I can some form where I can use the fact that f and g are not decreasing. So suppose I could write it in this form. So don't say equal to. Just notice what is this quantity going to do? Given that f and g are both increasing. The multiplication of those. Can I round this quantity? When both f and g are increasing, irrespective of what x1 x2 is. All I care about is positive and negative. How much is this? Positive always? Or this positive? Because if x1 is larger than x2, then both of them are going in the right direction. If they are negative, both are going in the direction. Product is always greater than equal.
Yes.
So now compare the last two things. Does this have anything to do with this? So this we know is greater than equal to 0. Now this quantity and this quantity, are they connected to each other? Is linear expectation. So there are 4 terms over there. You put a 1/2 in the front. F of x1, g of x2 is here. F of x1, g of x2 is here. Because the x2, x2, and x2, x2. Minus, make sure it's plus. And then the final one. Just put one. The punchline really is that because of f and g being increasing product irrespective of what x and x2 are. That is also there. So rest of it is, if you notice this, the rest of the proof can actually go backwards. The most important thing to notice is that two functions which will be going in the same direction is equal to the rest. That's the problem. Most proofs will go for back. We actually should think about how would I construct it. I would first notice a property possible. Okay. Using this, we want to claim our result. That now x is there's an x star. Now assume that it is true. Can you show that that is an x star?
This is at least expectation of that indicator.
Which one?
This fraction. Numerator, you can use this inequality. It's a protected x times indicator.
Yes.
Expectation of x times indicator is at least expectation of x times expectation of indicator.
Okay, very good. That will give you the answer.
It's at least expectation.
No, but you have to first ensure that we are increasing this. You establish that. See, if x increases, the indicator only increases. Right? You have to at least ensure that. Take nothing. Prove. That is simply this. Easier to define it for the existing. So this clearly is a non-decreasing function. This is also not decreasing. Okay, so now, so actually, it's not decreasing. Otherwise, if y increases, things can actually go on. Okay, so what do we have? For this lemma, what can I say? The expected value of
Why is this then?
is always greater than x. So if it's true for a fixed value of x, then as y increases, it's always true. Other way around is not true. This is greater than or less than. It's just probability of what. Which one? Is it true for?
So is the sign there correct in the definition of size pairs?
Yeah.
X less than.
It's pretty wide as well. I'm just writing so that you don't mix up too many. If you want, I can keep it now.
Probability y greater than equal to x is less than equal to.
Somehow we have to connect it to x star. What is the probability of x star is greater than little x?
1 minus.
Correct. So compare this to x itself. Now, what is probability? Star greater than little x. Is 1 minus of that? What is this telling you? Now, what can I say about P of x using this?
But sign in the indicator is different.
Okay,
Where it's less than or there is greater than.
fine.
We write indicator of x less than x as 1 minus indicator of x greater than x. Probability x star greater than x is greater than equal to probability x greater than x.
Keep you honest and let you do this. Okay, you've done everything. All you have to do is not even convince yourself, just put 2 plus 2 equal to 4 together. So which direction do you go for 4? Just to make sure that you remember the definition of stochastic down. This should be. I solved the rather than writing extra less than equal to writing extra greater. So this is a strong thing. Maybe easier to remember. Stronger means that this probability is larger than the weaker one. So this I will say. Oh. We're done everything. Even if you're not taking notes, you can just go back and look at the video. It should automatically happens. So from here, you just have to convince that you rewrite in a form that this is. Okay. So assuming that everybody knows marking inequality. And check share. Expecting on check. Remember?
Yes, so the probability x greater than a is less than equals to expected value of x by 1.
Very good. Missing something, we need to write.
X minus 1.
We expected.
Square. What is this?
Just this will also work.
Okay. Then something small something.
Variance of x by
This is an application. So to get this, you apply this and get it.
yes.
So what is variance of x? Divided by epsilon squared.
Epsilon.
Something is missing.
Epsilon is always positive.
That's not. It's too big. That's not what it is. Here also something is missing. It is not true always.
When X is
Positive. Non-negative. Okay, now just make sure that we cover this in class. What you want to do with the following. This also reminds us, see, turn off on is that. So, there. Yes. There. Where I will be. Down based on application the mark will actually give us. It's a normal. What it say, take L ID random variable that are 12. How much do they differ from their mean? Is unscaled multiple. There is no here. And that can be controlled by an exponential component. We call the rate function. Phi of A is called the rate function for the third. All right, can you prove this using markers? Just application one. Think about how to show. No. You want to show this using markers. That's okay. So no new ideas required. See, the only interesting part is that somehow it's falling as e to the minus n. That typically doesn't happen. So all the magic is sitting in this I of A. Which is essentially rewritten in a form where it looks like e to the minus n times I of A. And when I'm saying you only use Marcos, the inequality cannot be stronger than Marcos. So it's more or less a rewrite. So how do I rewrite this form? You have to start with what I have.
e to the power.
Right. Just exponentiate everything.
Yes.
Why can I do that?
Because
So it's equivalent to e to the summation xi. What is saying? Why is it so? So these are everything much. Two numbers. Because decreasing, this is no longer. Oh,
I was thinking xi should be positive or negative, that is also there.
not necessary. You want. So now what do I have? I can also multiply it if I wanted.
Yes.
This is for non-zero. Okay, T greater than 0. They want something like this, right?
Yes.
So T also has to appear. So for T greater than 0. Now what should I use? The only thing allowed is that. What do they imply?
E to the power t.
Then the magic thing is already appearing. What is that? What is this? That x is I. Yes. What is this? Again, I can keep this as it is. What can I do here? Some of the products exponent in it's a product inside px. So what would I write here? Something like e to the x side. Or I'll write, let me just say x, so that x is the same distribution as x1 through xn. How many of them?
Yeah.
T and n also, right? The sum of them. Yeah. So I have e to the minus n e to the power x to the power n of t. Now, what did I want? I wanted everything in terms of e to the minus n. So what do I do?
The P is a log of x.
Log. Log is not log. I don't want anything in log. Or you say, okay, for I of a, the form it is this, naturally asking to be written in a form log of expected value e to the power tx. So ta is already there. So you just raise it to the power, so you just rewrite it. Here. Okay. So rewrite. Okay, one example. Let example. Define it and or it's next. They like probably not. So it's actually evaluation of what we did, which are not. So we just evaluating this function I of a for this particular choice. It's not very deep. So I of a by our general form suprema. A now what is the distribution? Which quantity is it to include? So suppose xn is a binomial, let's say x1 is nothing but Bernoulli P.
What is IA for that? Expected value of p to the p into p to x1 is p times p to the g plus 1 minus p times p to the 0 the same thing. Okay. Now, if I know this, how do I do that? So what will be I on, let's see, I on x1 only. Oh. It simplifies. What value of t into this? So differentiate equal to so differentiation. Differentiate t a, so we get a minus log 1 by p times p. Then we say what a times is only e to the power 3. This is good. So e to the power 3. P also is common. Let's plant it back. Won't be very simple. Okay, very similar. Then we can go from x1 to x. By essentially saying that xn is nothing but summation of these x's. N of them. With one more inequality, this proof I'm not going to give for we might use it later. It's of similar flavor. There x I b but b it's in the book. X b b to the minus now. Proof is very similar to what we did. But at least remember this or go back. So it's in there. It's not very neither deep nor very difficult, but that might be useful in addition to which are not possible. See, again and again, we're doing lots of Bernoulli and binomial because the graph is going to look like Bernoulli and binomial. The discrete graph, and then we want to match it to Poisson somehow. So if in the background, we all want to collect all the results we want for the Bernoulli, binomial, and Poisson. So that time comes to writing graphs, we can just simply now use that. Okay, so let's stop here.